Yeah, as mentioned, I'm Khronos, I'm a council chair, and today I'm going to talk about Khronos and how it's positioning itself in the world of open source and machine learning and defining standards as well. So first, who knows what Khronos is? No one. Okay. Khronos is an international non-profit standard consortium defining graphic standards and compute standards to enable as efficient as possible graphics card use or compute use. Khronos itself got founded in the year 2000, so we realized it's 25 years old now, defining standards like OpenCL, Vulkan, or the quite old OpenGL. It's also defining standards like NNEF for neural network exchange transfers. And yeah, Khronos itself has around 160 members from all over the world. Around 40% of the members are in the US, 30% in Europe, and 30% in Asia, meaning it's a quite good distribution across the world. So before we start talking about what Khronos exactly does, it's important to define what an open standard is versus what open source is, so that we don't mix those two terms, which is other. So open standards are precisely defined specifications which define how software communicates with each other or how software communicates with hardware. It is really important to have a precise specification so that you can reliably implement a driver and then have a developer develop against this API, and then you have potentially hundreds of implementers, and you expect that your program will work perfect on each and every implementation. And this is ensured by open standards also defining conformance tests. And if you want to be conformance compliant, you have to run those conformance tests and prove that your implementation is compatible with the standard. On the other hand, and it's important, an open standard is a shared specification. So there's one specification only for one standard, but then a lot of vendors, people do implement this single specification. On the other side, you have open source, which is a collaborative effort to make a software project, or now OpenAI. You want to have as many people as possible do the implementation, and you want to have maybe a minimum number of implementations for a specific problem so that you don't waste too many resources getting this implementation. So it's a shared collaborative effort to get the best for the world in software. Yeah, and yeah, open standards are often used. So open source is quite often used within open standards to implement all the tooling you will need for a standard. If someone defines a standard and the standard doesn't have any tools to be used, and you have no tool to compile for a language, you don't have a library to load something for the standard, you can't export your PyTorch model to the standard, there's no one going to use your standard because, well, they have to do all the work on their own. And we want to have shared collaboration to do the work which can be shared to avoid all the friction. And also, if you have shared tools, you have less different software potentially exposing bugs you have to work around. It's just one piece of software you can rely on. So what are the benefits of open standards? Well, yeah, first, for companies, they really extend commercial activity. You have a network effect. If multiple companies support the same standard, then you can share resources. People who are learning the standard can work across multiple companies knowing already what to do. If every company would have something like the standard but defined on their own, they would have to relearn in each company how to use the APIs and relearn again and again. It creates too much friction. This way you reduce costs. Also, having a consortium to define a standard, you're reducing cost. If every company has a big team defining the standard, well, you have the cost in every company. If you're sending a few members of your company to a consortium and let those team members discuss with other companies, you're paying only for the few team members, and you get a spec which is probably even better because more people spend time on the single spec. Yeah, you want to avoid market friction with standards, so having interoperability. For the time to market, you can get faster if you're implementing a standard or if you're basing on a standard. Yeah, so essentially, standards are quite useful, and if you're defining standards, it's also important that the standard is being defined by an open consortium and not by a single company. If you have a single company defining a standard, then the standard will only apply things this single company wants to achieve. If you have an open wide consortium, then all the members have to agree on the single standard and work on it together. And so you get a better market penetration, including all the requirements of all the members of this consortium. And so, yeah, innovation is quite good, but if you are defining standards, you want to ensure that everyone can implement them, but at the same time, you don't want to over-specify a standard. If you would over-specify a standard, then you are limiting any kind of innovation within companies. All the Khronos standards have some kind of extensibility. So you have a core standard everyone can implement, but then one company is running slightly faster or wants to show something to the world, technologies, then it's possible to expose a new extension to the standard. And so the other vendors can implement it later on if they want to, but at least the technology is out in the world for everyone to test. And then even this way, you can get feedback, like ray tracing. NVIDIA released ray tracing extensions quite early. And then the feedback came from all the different software users. And then it got a Khronos extension with everything included everyone needs. So it was some kind of demo prototype, which then got a really good standard for everyone. So now that we know what standards are, why they are good, how does Khronos work? So within Khronos, we have working groups for each standard. And the working group members can only be full members of the Khronos organization, but anyone is welcome to get a member. You have to pay a fee to be a member so that you can contribute, but then you have a vote within the standards body if you're interested in a certain standard. Some of those working groups have technical subgroups. For example, the Vulkan working group is mostly graphics, but then there's a ray tracing technical subgroup, which discusses only ray tracing for the few people who are interested in defining ray tracing. There's no point that every member who is not interested in ray tracing goes to this technical subgroup. For machine learning, there's also a technical subgroup to define all the new extensions we need in Vulkan for machine learning and to discuss how we can improve Vulkan for machine learning. Then there's an adapter program within Khronos. So if you have a standard, you're interested in people adopting your standard, and to get a certified member, you pay the adapter fee, and then you're allowed to submit CTS tests to Khronos, and then you get on the Khronos certified list of implementations, and everyone can see that your standard or your implementation of the standard is certified. Another benefit is that within Khronos, there's an IP agreement that every company contributing to the standard don't do any IP infringement things to other members or adopters of the standard. So if you are using a standard from Khronos, you get the royalty-free patent licenses for the standard, and you don't have to worry about anything related to Khronos and IP. And the output of each of those working groups are first the specifications, of course, because that's what Khronos does. But since the specification alone is not sufficient, we also have tools, documentations, samples. Khronos members work on educator guidelines. We develop courseware materials. We go to conferences and educate people. And of course, we also have a big suite of conformance tests. And you don't have to pay to get to those conformance tests. The output of all those working group meetings is available to everyone on our GitHub page. So if you would want to implement, or if you would want to do your own Khronos standard implementation, you could do it. And once you are ready, you could come to Khronos and say, I want to be an adopter, and then submit your CTS. But you're not being forced to get adopter first, then you develop, and maybe figure out it's not working that well, and then you paid for nothing. So within Khronos, we try to be as open as possible in standard definition. Of course, because of the IP framework and confidential information of new features coming to APIs, we have an NDA agreement. So if a company is developing a new feature for hardware and we want to standardize it, we might not want to tell the whole world until the standard is ready, or you're building a new chip which gets released in a year and you need changes inside the API or enhancement, not changes, everything is stable. Then you want to talk to other hardware vendors if they have interest in implementing the same changes. So everything within a working group is NDA confidential and cannot be carried outside of this working group. Then we have advisory panels. Those are also under NDA and the IP framework, but they don't get, they can't get to the working group meetings, but they are valuable to provide input in requirements to the standards, and they even are allowed to draft specifications, for example, for new extensions within the standard. Then the output of all of those is provided as open source, which is the yellow circle. Everyone can download, file issues, and then we have Khronos meetups and chat forums and a machine learning forum as well. You can join, and then you can ask questions within the Slack or Discord and ask, oh, I'm trying to do this in Vulkan. It doesn't work. Okay, then someone hopefully is going to answer you. Or even you can say, okay, I would want to have some feature, and maybe you find some who is interested. So for the active standards itself at Khronos, so we are here in an AI conference, so we are mostly interested in parallel compute standards, which can run AI. And we have Vulkan, OpenCL, SYCL as real compute APIs. So Vulkan can graphics as well, but it has full compute support. SPIR-V is quite interesting because it's a standard AR which is binary stable, meaning you can get new tools, but you can always generate SPIR-Vs for our drivers. We have now completely new Slang as open source shading language compiler, I will talk about later. We have OpenVX as parallel computing graph API. NNEF is embedded into OpenVX as extension, and then we have for Vulkan, OpenGL, and SYCL safety critical versions of the APIs. If you want to put them in a car or a plane, you don't want them to crash. So you want to ensure that there's nothing which can cause something like that. So Khronos has a GitHub repository, and we currently have about 181 projects within Khronos showing how important open source is for Khronos. Of course, there are specifications for each and every standard, and some of them are now in an XML spec so that you can parse them, generate your API bindings. The whole spec language, which can be generated to ASCII doc or PDF, is available if you want to have something different. All the conformance test suites to test and confirm API functionality is available. It can also be a sample if you want to know how something is really working. Having this open source enables really early and pre-conformant testing to anyone who's interested in those standards. And we have the full API ecosystem support with educational samples, loaders and layers for APIs where you need to load the APIs through some special mechanism. Layers sometimes allow to add functionality to an API or intercept API calls to introduce something in between, also quite often used in Vulkan. Utility libraries like, I like Vulkan, sorry, so this is what I use often. For Vulkan, people say it's really complex to do graphics. Compute is not that terrible. Getting started takes a lot of lines of code, so people started to make something like Vulkan Bootstrap, which takes all the utility functions and just brings you faster up to speed. And of course, we have a lot of language compilers. All of those compute APIs need input, and input for compute is a shader or a compute kernel, so we have to compile those. And we don't want to have a shading language within a driver, if possible. So something like that was in the past for OpenGL. There was GLSL. I was working on GLSL drivers and did also a lot of implementation. If a compiler for a language is within a driver and you have multiple implementers, then there's a risk that the standard is not fully implemented in ways which are not yet tested. So what is if your application allows something which is not defined in the standard? And well, then people had problems if a new driver came out, the driver got more conformant, and then an old shader didn't work anymore. This is non-ideal. Now, all shading languages are outsourced to real compilers with PV as intermediate language, which is fully specified and really good tested. And you have a choice of multiple languages now and not only a single one, like in OpenGL, which makes it a really good ecosystem for your use cases. And of course, everyone is invited to go to the GitHub repository and file issues if you find any issues in our samples, tests, or even specifications. If the language is not clear, you can file an issue and telling, okay, on section 3.2.1, you are writing this, and it doesn't work this way. And then, yeah, someone will take a look at it and respond, hopefully, most likely, and the issues will get fixed in those specs. And for the samples, you can even file PRs if you sign the Khronos Apache 2.0 CLA. If you want to write own samples and contribute them, you are welcome. So the more samples we have, the better for everyone to use the standard. So the newest addition to Khronos is Slang. Has anyone ever heard of Slang? Oh, okay, that's better. So Slang is an open source shading language, originally developed by multiple people and NVIDIA. It has been hosted at NVIDIA since 2017, but it was basically single company governed, but an open source project. Now Khronos decided to adopt Slang, and the whole Slang project got transitioned over to Khronos. And now it's under multi-company open governance, so that not a single company is controlling the Slang language anymore. The Slang compiler itself is able to compile multiple languages to SPIR-V, but also other languages, and so quite powerful. So all the technical work is now streamlined under this open source project. And more important, so far for Khronos, the spec was a product of Khronos and all the tooling was required for the spec. Now Khronos has the open source project as Slang as open source project, and the specification will be a side product. So Slang didn't have a full specification, but the full specification is now being worked on, but the source code is the thing which defines how it works at the moment. So for Slang itself, Slang is a compiler, but Slang is also a language, which is better fit than C++ for graphics and compute on GPUs. Slang as compiler also support HLSL 2020 and GLSL. So a lot of companies have a huge legacy code base, and they are interested in porting to Slang. And by allowing Slang to consume the old code base, we allow them to have a transition path. You don't have to translate your whole shading base to Slang in one step. You can start with the most important shaders, or you can just bring all new shaders to Slang and slowly migrate over from older shaders to Slang. Or maybe they're getting so old that you don't need them anymore. And Slang itself is a universal compiler somewhat. It can compile to SPIR-V, which is required for Khronos. SPIR-V is the input to our graphics and compute API Vulkan. But it can also go to GLSL or HLSL if you are going to write code against Microsoft DirectX. You can compile for Apple's MSL if you are on Apple. If you have a web GPU application, you can use Slang to generate your web GPU shaders. Slang supports PyTorch, C. If you have CPU code, CUDA, and optics as well. So Slang is really like some universal shading language and compute compiler for everyone. And now it's really under open governance. So why is Slang in this talk? Because it's a shading language mostly, but supports compute. Slang has an auto-diff feature, so it can automatically differentiate code. And if you have been writing your own custom operators in PyTorch, you know that for each forward operator you're implementing, you always have to write the backward operation. And you have to keep the forward and the backward operation always in sync. If you don't, you get strange results and your networks might not train properly anymore. With Slang, you can just write the forward operator and let Slang generate the backward path for you. And so you're always automatically in sync. Awesome. If you're interested in Slang, you can take a picture of the QR code on the slide. Shannon Woods did a pretty good presentation at the last Vulcanized event about Slang for neural graphics. And she gives a full deep depth insight how Slang can be used for neural graphics. And quite interestingly, the time Slang got transitioned to Khronos, the interest in Slang raised a lot, showing that having something under open governance is really helping the language a lot. So if you're looking at stars over time, and the yellow curve is Slang, and at the time Slang got to Khronos, the star count just bumped up increasingly and now has more stars than the DirectX shader compiler or GLSL Lang from Khronos itself. So with a shading language in place to do machine learning, now we get to the Khronos Compute Acceleration APIs. We have APIs at multiple levels, depending on how much control you want to have over the hardware. Higher languages and APIs are NNEF, as Neural Network Exchange Format, OpenVX as graph-based vision and inferencing acceleration framework, of course Slang as shading language, and SYCL as single source programming language and API. So with SYCL you can write single source code like in CUDA and compile it down usually to OpenCL. This is the main backend, and then OpenGL is the runtime for the SYCL code. But there are also SYCL compilers to CUDA and CPU and everywhere you want to do your parallel distributed work. And then we have lower level APIs. So there's SPIRV as input for the kernels you wrote or the shading. And SPIRV can be consumed at the moment by Vulkan, Vulkan SC, or OpenCL. If you're going for Vulkan at the moment, Vulkan supports only GPUs, but OpenCL on the other side supports GPUs, DSPs, CPUs, FPGAs, custom hardware, AI hardware, everything you can imagine. There are a lot of OpenCL backends out in the world, mostly in the mobile space and less on the desktop space. So now I want to talk about a little bit about the APIs to present them so that you know what they do. First, the SPIRV intermediate presentation is a compiler target for graphics shader and compute kernel programs because we want to ensure best compatibility within drivers, and we don't want to force people to use languages defined by us. We just want to enable people to use compute and graphics in our APIs, and the languages should be defined externally so that they can enhance and improve over time without harming our implementations of the standards. This encourages a really rich compiler ecosystem because now we decoupled the shading language itself from our APIs. If you want to write a new shader because you have an idea for an awesome machine learning compiler which can generate awesome compute kernels, you're free to do it. You compile to Slang and then everything works on all implementations which are conformant to Slang, to SPIRV. Some people might wonder why we are not using LLVM IR. And actually, the first Spear implementation, without a V at the end, did use LLVM IR. And well, the problem was LLVM was not version stable. And this way it was not a standard we could rely on. If you got a new LLVM version, the output binary of this new LLVM version got a version bump. And a newer LLVM compiler was not able to generate an older LLVM binary anymore. But now imagine you have drivers out in the world which do not know about this new LLVM version. You will not be able to consume the output of a new LLVM compiler because it has a version bump and might have changes not known by the older driver or your older implementation. So because of this, this happened twice. The Khronos group decided, okay, we have to define our own standard intermediate representation, which does not have those problems. It must be binary stable forever, unless we make new versions, of course, but this is not happening or really tiny, but the binary compatibility is given. And also LLVM has something called bitcode, which means it has a bit stream, which is not easy to pass, but inside drivers, you want to have more simple code to avoid errors, security flaws, and all the stuff. So SPV is using really byte-based decoding, and so all the bitcode magic goes away, and it's a simpler standard. You can read and write with simpler tools. And yeah, since tooling is important, SPV has SPV tools, which has an API, and it also contains a lot of commands for SPV processing, and SPV Cross, which is a tool to provide reflection, and which can also generate a human-readable disassembly to GLSL, HSL, and MSL if you want to understand the shaders you have generated later on, or if you want to transpile them. How do people know, for example, about DirectX on top of Vulkan? On Linux, you have Proton, where you have HLSL shader input, but you need to transpile HLSL input to something consumable by Vulkan, because on Linux you don't have DirectX, of course. And SPV Cross can be used for tasks like this. So it's really a shader transpiler for all your use cases for our standards. And so SPV support itself is growing a lot. So there are three main compilers: the Khronos GLSlang, which was a GLSL reference compiler and validator to ensure that your GLSL code is really conformant. Microsoft DirectX C compiler can compile HLSL to SPV, and the Khronos Slang compiler can compile Slang, GLSL, and HLSL 2020 to SPV as well. And for the happiness of everyone, Microsoft is adopting SPV as well. Microsoft Shader Model 7 will be based on SPV, so everyone who is doing cross-platform work now has a single compiler for their shaders. Pretty good. And also LLVM 20 now is promoting a SPV as official backend. So you get all the LLVM features without the LLVM pane as open standard with drivers which cannot move at the same speed with LLVM. So for the ecosystem itself, just a small graphics showing how the whole ecosystem works. So we have the blue boxes, which are language definitions. We have Slang, HSL, GLSL, but also for OpenCL, there's OpenCL C as C-like language for compute, OpenCL C++, HIP and CUDA compilers are available. And all of those go through either Khronos open source projects, which are the yellow boxes, or third-party open source projects, which are the red boxes. And SPV is in the center of all this, and then can give the output to either SPV Cross if you want to transpile, or to Vulkan or OpenCL. And one thing we have to mention, currently SPV has two different flavors. It has one flavor for OpenCL compute and one flavor for Vulkan, because on Vulkan we do not support pointers yet. OpenCL has more control over precision if you want to do rounding modes, and some better flow control. But all of this will hopefully be worked on so that we have a single SPV flavor only in the future. And yeah, talking about open source projects, Khronos standards are used a lot to layer between different APIs. For example, the Vulkan API is so low level that you can put nearly every other API in the graphics and compute world on top of Vulkan. But you can use Vulkan also to implement OpenGL, DirectX, or Metal. So basically, once you have some Khronos API, you can move nearly everywhere else with open source APIs or with open source libraries which implement those APIs. And we really endorse open source for Khronos APIs. So if you want to implement a Khronos standard as open source project, as community open source project to be exact, then we are giving you an adoptership so that you can run your open source implementation against the Khronos conformance test and submit it. And for example, there are multiple OpenCL standards implemented on top of Vulkan and Mesa, and those projects have CTS conformance tests, so they are guaranteed conformant to the standard. So coming to the next language, OpenCL. OpenCL is a low-level parallel programming API and runtime, so that you can offload your CPU code to GPUs, DSPs, FPGA CPUs. It has a platform layer API. You might have multiple OpenCL devices in your system, and you need to choose an OpenCL device, query the capabilities, and then start running code on it. And for this, there's a runtime API where you can build your OpenCL code or import the SPV shaders and run those. And OpenCL itself has some quite explicit application control. You can decide what to execute on which device, where you store all your data, and also you can define a dependency graph so that the OpenCL runtime can resolve it and do all the synchronization between the nodes in these dependencies. And it's still under active development to get better and better. OpenCL is used in quite a few frameworks for machine learning and ML compilers. It's not used that much on embedded or mobile markets at the moment. It's more often used in embedded and mobile markets, so mobile phones or automotive, where people need a reliable compute platform. And it's also integrated in frameworks like Glow or MMN from Alibaba, Paddle by Baidu. There's an TVM Apache implementation. On Android, you have LightRT, which uses OpenCL. So it's quite actively used on non-desktop. On desktop, you could use a layer OpenCL on top of Vulkan, and then you would have a full OpenCL 3 implementation as well. Next, there's NNEF, which is a neural network exchange format. Khronos realized that we need some kind of neural network exchange format for our APIs. And a few years ago, a few people started a new working group to define it. It's open royalty-free standard to represent neural network models. It's designed with a human readable syntax so that you are able to write your network in a text editor if you want to. The rates, of course, not. This would be too much. And it's built for future extensibility to support new advancement. And we also provide open source tools for parsing, validation, conversion to and from NNEF, like a PyTorch exporter. But NNEF itself does not define a runtime API by itself. Currently, OpenVX has an NNEF extension, and every OpenVX implementation which implements this extension can run NNEF networks. Finally, for compute-only APIs, there's SYCL, which is a single-source C++ heterogeneous compute API, where you can have a single source file and you could put in your C++ code and describe how it's being executed. And then you can run this one of the SYCL compilers, which is implementing the standard, and you get a binary which can then run on any SYCL supported device, or OpenCL is one of the backends of SYCL. And you don't have to take care of this. I have to load shaders and manage shaders and do all the stuff you have in Vulkan Compute, for example, or OpenGL Compute. So SYCL's focus is really developer productivity, single source, compilation, execution, and you are done without a lot of boilerplate code around. SYCL itself implements much of the parallel computing, parallel programming model of OpenCL for tasks and dependencies. And it's also used in a few frameworks like PyTorch has a backend since version 2.4. Llama CPP has a SYCL backend for Intel, AMD, and NVIDIA GPUs at least. The UXL Foundation is building some compute ecosystem around SYCL by providing a 1DNL library for primitives in deep learning. And there's Cyclops, which is using SYCL to target novel RISC-V-based AI accelerators as well. And finally, there's Vulkan for ML inferencing. So Vulkan Compute is used more and more in the world. And Vulkan itself is widely adopted in mobile, embedded desktop, and cloud platforms. And there are native drivers for Windows, Linux, Android, and the Nintendo Switch. So nearly everywhere. And with Molten VK, which is an implementation of Vulkan on top of MSL, you have Apple support as well. And it's conformant. And in Vulkan, we are spending a lot of time now on thinking about how can we extend Vulkan so that machine learning or inferencing works pretty well on Vulkan, because professional applications want to use neural networks now and implement them, or gaming wants to use more and more machine learning as well now. But for gaming, you cannot force any game developer to use CUDA, because it would be NVIDIA only, and the game has to run anywhere, everywhere, and as long as possible. So we have now defined matrix multiply in a subgroup, like CUDA tensor cores. Then there's a more enhanced version of this where the whole group within a compute kernel, so multiple subgroups, work together on a bigger tile. And this takes care of all the scheduling and loading and sharing of data in the full group. There's a cooperative vector extension for more efficient matrix vector implementations, and this one also supports FP8 now and FP16 and 8. SPIR-V itself does not define those formats yet. And yeah, there are extensions for precision for bfloat 16 and float 16 and 8. And yeah, we are surely working on more formats in the future to allow more ML workloads to be run on Vulkan. And Vulkan is being used increasingly for backend acceleration in inference frameworks. Everyone might know GGML, so Llama CPP has a pretty good Vulkan backend now. There's PyTorch, ExecuTorch for the PyTorch Edge strategy, which has a Vulkan backend. The TVM Apache compiler supports Vulkan. IRI is a graph compiler which imports Onyx, TOSA, a few other formats, and can target Vulkan as well, including cooperative matrices to get tensor core support. And then there are frameworks from MCCN, from Tencent, NCCN, MNN, LightIT has Vulkan support, and AILA Inc. also has an inference backend, which is not open source, with Vulkan support. So now that we know everything about Khronos, how does the ecosystem now work? So we have a few open source frameworks, PyTorch, TensorFlow, PaddlePaddle as example, and Llama CPP, and those utilize compilers and runtimes. There are proprietary compilers and runtimes like TensorRT, there's Onyx runtime, OpenVino, LightIT, but also ExecuTorch. And we have a lot of arrows going there, which means there's a lot of confusion, most likely for a lot of developers, which library to use. But the even bigger confusion is those compilers and runtimes and libraries now have to go to hardware, and so they have to use acceleration APIs. And for simplicity, this does not include any acceleration APIs for NPUs, because For each and every NPU vendor, I found at least one library. For some, I found 2 or 3 different libraries, depending on which hardware you're using, or if they decided to deprecate an old version and make a new library instead of thinking about how to make this library work better. Yeah, it's really chaotic. And so, yeah, the question is which compilers, runtimes, and libraries are being used is something which is really of interest for Khronos, because now we want to start machine learning market research. We, as Khronos Group, are wondering within the ML Council if Khronos can do anything to reduce this market friction and complexity. Can we make a new API, or can we enhance the Khronos API better to support machine learning? What are the real industry needs that would have been met if Khronos would define such an API? Yeah, do we need some common hardware actuation stack across CPUs, NPUs, and GPUs and other accelerators? And most important, can we achieve some kind of performance portability across device hardware architectures? I'm not sure how many of you already tried to write gem or convolution on your own. If you try to do it, you really get super fast and working implementation. But then you realize, okay, this is super slow. So you start on optimizing it, and you have one specific CPU or GPU, and you manage to get to 50, 60, 70% speed of light, maybe quite quick. But then it gets more and more time consumed to get faster. And now you go to a different hardware. Like you spend all your time on NVIDIA and go to AMD, and you figure out, oh, on AMD, hardware is different, and they have different, I don't know, latency for RAM, different cache size. Now all the optimization starts again. But now, well, Qualcomm is now Windows on ARM vendor. So there's a new GPU available for your game. So you have to do the work again. And tomorrow, a new vendor will come in because Windows ARM might get a thing in the future. At least more and more vendors are trying to get there. And you would have to optimize all your compute shaders for each and every architecture. And now multiply this by the amount of frameworks and imagine how many man-hours goes just implementing those simple operations, which should be supported by the hardware. And then we are not talking about the support for NPUs. If you would want to support an NPU, which is supposedly super energy efficient, which is extremely important if you have a mobile device or your notebook, yeah, there's no standard for NPU support, not a real one which is portable for every operating system. Yeah, and how do we solve this? Would it make sense for Khronos to explore options? So one thing I have on my personal mind is a graph API the way to go? Thinking about how do ML networks work and how all the tiling work, going to compute only, is this sufficient, or do we really have to define a graph API for hardware? And if we have to go this way, the problem is how to define this graph API. Because we want to run everywhere, we want to have efficient tiling, and we want to allow fusion, and we want to have this performance portability, which is extremely hard to achieve as of today with compute shaders. And the goal is also to have performance portability in the future. So you are designing your applications for hardware today, but it is not unlikely that your application will be used on hardware tomorrow as well, and you don't want to spend all the engineering efforts again to get to speed of light. So if graph APIs would be the thing to go for an accelerator API, then what kind of operator sets do we have to support? Currently, I'm aware of NNEF, TOSA, Onyx, or A10. Is there something else we should do? The problem is if we would go for Onyx, it's too fast moving. It's like LLVM. It's not stable enough for standard, most likely. NNEF is Khronos defined, but this is not major yet for everything. TOSA, I can't comment on, and A10 is PyTorch open source, so not a standard. Is there something we would need to define? Could we work with those organizations? We will have to figure it out. Also, the ML space is moving fast. So can we get away with pure operators? Can we have some minimal set we can use to implement everything or not? Probably not. So there must be a way to have your own custom operators. Once you have custom operators, so some kind of compute which can generate tiles, you would be able to enhance the standard on your needs. If you have a new custom quantization format, if it's not defined by the Graph API we would expose, then you wouldn't be able to use it. You would have to convert everything to something supported by the hardware, and then you might have lost the benefit of the new quantization layout for memory reduction on the GPU or NPU. You still could save storage on disk, but most likely storage on disk is less of a problem than storage on the compute device. How can we handle generic quantization? I guess an API would have to do this. And to know what we should do, we are starting an Khronos Group AI opportunity survey, and there's a link as well. It would be really great if any of you could take a picture, take the time and fill it out. This is an initial survey just to get some information about what frameworks people use and what ML use cases they have. There will be a follow-up later on, if you agree to, where we are going to ask more detailed questions about what Khronos should do if they do anything. So that's all from my side. Thank you for your time and participation. And yeah, please participate in the survey. Everyone is welcome to join Khronos to influence standards on khronos.org/members. You can write an email to memberservices@khronos.org as well if you want to get a member. And if you want to contact me for questions about potential machine learning APIs in Khronos, just send me an email and I try to give you a good answer or forward your inquiry to people who can help you. Thank you very much.